the Ethiopian Educational Information and Communication Technology presents Educational Satellite Television Programs.
Hello, teacher. Hello, students. Welcome to today's lesson on metallic bonding. Previously, we discussed dispersion forces. We learned how dispersion forces are formed, and we discussed examples of different substances that experience them. We learned that if it were not for this attractive force acting between non-polar molecules and atoms, then these molecules and atoms would remain in the gaseous state rather than condensing and solidifying. We also learned that dispersion forces affect the melting and boiling point of substances. Larger atoms and molecules tend to respond to stronger dispersion forces and thus have higher melting and boiling points. In today's lesson, we will discuss another type of force known as metallic bonding. We will explain how metallic bonds are formed, and we will look at some examples. We will also talk about the electron-C model. Let us begin. Metallic bonding refers to the bonds that occur between metal atoms. It can also be defined as the interaction between positive metal ions and delocalized electrons. Students, I am sure you recall that delocalized electrons are electrons in a molecule or solid metal that are not associated with a single atom or covalent bond. These electrons are also referred to as conduction electrons. The positive metal ions are also referred to as kernels. Therefore, metallic bonding can be imagined as a sea of electrons in which positive metal ions are embedded. Or, in other words, metallic bonding is the electrostatic attraction between a sea of conduction electrons and the kernels within metals. Let us discuss the electron-C model further. The electron-C model of metallic bonding proposes that all the metal atoms in a sample contribute their valence electrons to form a sea of electrons. The sea that forms is not localized for any particular atom. The bonding electrons are able to move freely throughout the three-dimensional structure. the metal ions are suspended within the electron C in an orderly arrangement. Remember, students, metallic bonding occurs between elements on the left side of the periodic table. Metallic bonding accounts for many of the physical properties of metals, such as their strength, malleability, ductility, thermal and electrical conductivity, and luster. We will be talking more about this in our next lesson. Students, how is metallic bonding different from ionic bonding and covalent bonding? Please discuss this with a partner, and I will see you in a few minutes.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Welcome back, students. I am sure that you and your partner had a very interesting discussion. In contrast to ionic bonding, the metal ions in metallic bonding are not held in place as rigidly as they are in ionic solids. In contrast to covalent bonding, metallic bonding does not involve any particular pair of metal atoms that is bonded through any localized pair of electrons. Instead, the valence electrons are shared by all of the atoms in the substance. The substance is held together by the attraction that exists between the positively charged metal ions and the mobile, highly delocalized electrons. While an electron pair in a covalent resonance hybrid is delocalized over a few atoms, the delocalization that exists in metal is much greater. Did you and your partner talk about these points during your discussion? If so, you are correct. While the term metallic bond is often used to contrast the term covalent bond, it is preferable to use the term metallic bonding. This is because there is really no such thing as a single metallic bond. Metallic bonding is collective in nature. It is also important to note that not all metals exhibit metallic bonding. For example, the mercurous ion forms covalent metal-metal bonds. Let us continue our lesson by discussing the strength of metallic bonds. The strength of metallic bonds is dependent upon a couple of factors. The first is the number of electrons that are present in the delocalized sea of electrons. If the sea contains more of these electrons, then the resultant bond will be stronger and the melting point of the substance will be higher. The packing arrangement of the metal atoms also affects the strength of metallic bonds. If the atoms are more closely packed together, then the resultant bond will be stronger, and the melting point of the substance will be higher. Students, we have time for one last activity. Please answer the following questions. How are metallic bonds formed? What is the electron sea model?
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Hello again, students. Did you have any trouble answering these questions? Metallic bonds are formed when the valence electrons of metal atoms are released to form a sea of electrons. This freely moving sea of electrons holds together the ordered pattern of positively charged metal ions. The electron sea model is a concept used to describe how all the metal atoms in a sample of metal contribute their electrons to form a delocalized sea of electrons. This sea of electrons envelops the positively charged metal ions. Students, if you have any questions about this lesson, please direct them to your teacher. Also, remember to review your notes after this lesson, as well as after all of your other lessons. It will help you to retain information, and it will further your studies. In today's lesson, we discussed metallic bonding. We learned that these bonds are formed because of the attraction between positive metal ions and delocalized electrons. We learned that this type of bonding can affect the melting point of metals, as well as certain physical properties, such as strength, malleability, and conductivity. In our next lesson, we will learn more about the properties of metals in relation to the concept of bonding. This brings us to the end of our lesson for today. Until next time, thank you, teacher. Thank you, students.